Hi, my name is David Stalfa. I'm a PhD student at Northeastern University, and today I'll be presenting results in the area of flow scheduling.
The title of our paper is Scheduling Flows on a Switch to Optimize Response Times. This is joint work with Hamidreza Jahanjou at Google and Rajmohan Rajaraman at Northeastern University. We first motivate our problem with the following example. Suppose we have a data center with servers that communicate with one another. In each round of communication, say every minute, a server can send some data to other servers via its output port and receive data from other servers via its input port. Each output port, shown in blue in the figure, has a limit on the amount of data it can send, in this case, say 3 gigabytes. Similarly, each input port, shown in orange, has a limit on the amount of data it can receive, in this case, 5 gigabytes. What we would like to do is schedule each round so that the data transfers aren't waiting too long to be executed. We model the data center as a complete bipartite graph, or switch, with output ports, shown in blue, and input ports, shown in orange. Each port P is labeled with its capacity, which we denote CP. In a single round, we have a set of requests or flows represented as edges, waiting to be fulfilled. Each request E has an associated demand DE, shown as a box on its edge. We can schedule requests to execute in this round on the condition that the sum of demands scheduled on any port is less than the capacity of that port. In the figure, bold edges represent those requests that are available to schedule in this round, and green shaded edges show those requests which we actually schedule in this round. In each round, we schedule a subset of the requests received so far, subject to the port capacity constraints. If a request is available to schedule in any round, then it is available in all subsequent rounds until it has been scheduled. The response time of a request is the total number of rounds in which a request is available and has not been scheduled in a previous round. We note that in the literature, response time is also sometimes known as flow time. In the figure, the received requests are depicted on the left, and the schedule in each round is shown on the right. We can see that edge E arrives in round 1 and is scheduled in round 3, so its response time is 3. For our results, we focus on minimizing two objectives related to response time: the average response time and the maximum response time. We allow for resource augmentation, meaning we allow our algorithms to increase the capacity of any port. We also consider two settings: the offline setting, where all requests with their release times and demands are known in advance, and the online setting, where we learn of requests as they arrive. Our main results are in the offline setting, but we obtained several theoretical and experimental results in the online setting as well. Our first main result is an offline approximation algorithm with resource augmentation for average response time over unit demand requests. Our algorithm achieves an average response time of O log n divided by C times the optimal, and increases port capacity by a factor of 1 plus C, where C is any positive integer. This result is obtained using an LP relaxation and iterative rounding. Our second main result is an offline algorithm with resource augmentation for maximum response time. This algorithm achieves optimal maximum response time and increases port capacity by 2 Dmax minus 1, where Dmax is the largest demand on any request. This result is obtained using an LP relaxation and rounding procedure. Our main theoretical results in the online setting include an extension of our offline algorithm for maximum response time. The algorithm achieves maximum response time within O1 of the offline optimal and increases the capacity of each port P to 2CP plus 2Dmax minus 1, where again Dmax is the largest demand on any request. We also give lower bounds on the competitiveness of any online algorithm for either average or maximum response time without resource augmentation. For our experimental results, we provide the outcome of experiments on several heuristics for average and maximum response time. We compare the performance of these heuristics against each other and against the LP values. We include here prior and independent related results. Much of the prior work has been in the field of multiprocessor scheduling, in which, unlike our problem, machines are not embedded in a network topology. I will first discuss related work on the average response time metric. In standard multiprocessor scheduling, versions of the problem with a single machine have been shown to be polynomial time solvable. Other versions, even with just two identical machines, have been shown NP hard. Leonardi and Raz give a competitive algorithm for one problem where the number of machines is held constant. The iterative rounding technique we use in our average response time result is derived from Garg and Kumar and Bensal and Kulkarni, who use the result to give offline and online algorithms for minimizing average response times in the multiprocessor setting. In recent independent work, Dinitz and Mosley prove a result in a slightly different model, but their results entail an 0.1 average response time approximation in our model, with capacity blowup of at least a factor of 3. Our algorithm achieves a log n approximation and requires capacity blowup of 2. For maximum response time, the multiprocessor scheduling problem with identical machines has been shown to be polynomial time solvable, and the first in, first out heuristic is known to be competitive for constant machines. Also, Bensal and Kulkarni give an approximation for maximum response times on unrelated machines. We first consider the maximum response time objective in the offline setting. Our first result is showing that maximum response time is hard to approximate to within a factor of 4/3, assuming p is not equal to np. The proof is by reduction from the timetable problem, shown NP hard by Evan, Itai, and Shamir. In the timetable problem, we schedule teachers to instruct students such that both teacher and student are free when they are scheduled to meet. Teacher T and student S meet for at least a given time RST. No teacher meets with more than one student at a time, and no student meets with more than one teacher at a time. The reduction models this problem as a bipartite graph, with teachers on one side and students on the other, and the challenge is to structure the edges to match the timing restrictions of the timetable problem. For this, we refer to the paper. To approximate maximum response time, we relax the problem to allow requests to be available in non-contiguous rounds. We call the resulting problem time-constrained scheduling, and we formulate the problem with the shown linear program. In the linear program, the XET variables indicate the amount of request E scheduled in round T. RE is the set of rounds in which request E is available to schedule, and DE is the demand on request E. FP is the set of requests adjacent to port P, and CP is the capacity of port P. The first constraint states that the sum of demands scheduled on a given port in a given round must not exceed the capacity of that port. The second constraint states that a given request must be entirely scheduled over its available rounds. Given a solution to the time-constrained program, we round the solution using a lemma from Karp, Layton, and Rivest. The lemma entails that a fractional solution can be rounded to an integral solution in which the capacity coefficients are increased by at most 2 Dmax minus 1. This entails that for a given instance of the LP, we can either determine that it is infeasible or produce a valid schedule in which the capacity of each port has been increased by at most 2 dmax minus 1. By binary searching on the response time, we can optimize the maximum response time metric. This entails our maximum response time main result. Note that in the case of unit demand requests, where we increase capacity by 1, this approximation is tight by our hardness result. We now discuss optimizing the average response time metric in the offline setting. In this section, we assume for simplicity that all port capacities and all request demands are unit. We formulate a simple linear program that serves as the basis for the linear program formulation we actually use. In this program, the variables x, e, t again indicate the amount of request E scheduled in round T. Fp is the set of requests adjacent to port P, and Re is the release time of request E. The objective function corresponds to the average response time of the solution. The first constraint states that each request must be entirely scheduled, and the second constraint states that the total demand on any port at any time is at most 1. Our linear programming formulation uses a series of linear programs, starting with this base program LP0. LP0 relaxes the previous simple program to constrain the load over an interval of rounds, rather than over individual rounds. Note that the objective function and first constraint are identical to the simple program. The only difference is the second constraint, which states that the total demand scheduled over 4 rounds is at most 4. Given a solution to LP0, we reduce the size of the problem as follows. We first remove all variables given the value 0 in the solution. We fix the assignment of any integrally assigned requests and remove all variables related to those requests. For a given port P, we order the variables related to requests adjacent to P by increasing values of T. We define the sets IP11, IP21, IP31, etc. as the shortest successive sequences in this order that sum to greater than 4. We define the iterated program LP1 using these sets IPA1. Again, the objective and first constraint are identical. The new third constraint states that for a given IPA1, the sum of variables in this set is upper bounded by the sum of variables in this set given their values in the solution to LP0. We generalize this procedure in program formulation and present the generalized program LPL. Again, the third constraint states that for a given IPAL, the sum of variables in this set is upper bounded by the sum of variables in this set given their values in the solution to LPL minus 1. In the paper, we show that with each iteration L, the number of requests considered in the program LPL is reduced by a factor of 2. This entails that there are at most log n iterations, and that the total load given by the successive solutions on any interval is at most a log n factor over the capacity of that interval. To construct a schedule from the resulting assignment, we divide the schedule into intervals of size O log n. Using the Birkhoff-von Neumann theorem, we decompose the requests in each interval into a series of at most O log n B matchings. We schedule the B matchings in each interval, starting with the earliest. This procedure results in no request being delayed by more than O log n over C rounds for any integer C greater than 0. This entails our main result regarding average response time. For any C greater than 0, we can compute in polynomial time a 1 plus O log n over C approximation for average response time over unit size requests, while incurring a blow up in capacity by a factor of 1 plus C. We now discuss theoretical and experimental results in the online setting. We first show lower bounds on the competitiveness of any online algorithm for either average or maximum completion time without resource augmentation. In the lower bound constructions, all ports have unit capacity and all requests have unit demands. Figure A gives the lower bound construction for average response time due to Jahanjou Kulkarni. The solid edges appear in each of the first T rounds, and the dashed edges appear in the subsequent M rounds, where M is much larger than T. An optimal solution will schedule all of edges 1, 3 in the first T rounds, and then schedule the remaining 1, 2 edges in parallel with the first T instances of edge 4, 3. This entails that only T edges are delayed by T rounds. However, any online algorithm will, at best, leave half the 1, 3 edges remaining after T rounds, which entails that M edges are delayed by T over 2 rounds. This yields an arbitrarily large competitive ratio. Figure B depicts the lower bound instance for maximum response time. In this instance, the solid edges are released in the first round, and the dashed edges in the second. An optimal solution is to schedule 1, 3, and 4, 5 in the first round, 4, 6, 1, 2, and 7, 3 in the second, and 7, 5 in the third. This yields a response time of 2. However, since the dashed edges can be chosen adversarially, the best online algorithm can achieve a response time of 3. Our next theoretical result in the online setting is a competitive online algorithm for maximum response time with resource augmentation. The algorithm uses a guessed maximum response time row and waits for row steps, scheduling nothing. After row steps, it batches all unscheduled jobs and attempts to schedule them using the offline algorithm. If the instance is infeasible, the algorithm increments row and continues to wait. Otherwise, it schedules the request in the subsequent rounds. Since the offline algorithm achieves optimal response time, we know that all batched jobs complete after 2 row rounds. Further, the capacity needed on each port is no more than double what is needed for the offline algorithm. This entails the theorem that there is an online algorithm that achieves maximum response time at most double the offline optimal, and for which the capacity of each port P is increased to 2 CP plus 2 Dmax minus 1, where Dmax is the largest demand on any request. Our experimental analysis focuses on 3 heuristics for flow scheduling. The first, MaxCard, schedules a maximum cardinality matching in each round, regardless of how long each request has been waiting to be scheduled. Surprisingly, this heuristic performed well for average response time. The second, min-r-time, weights edges by how long they've been waiting, and schedules a maximum weight matching in each round. This heuristic works well for maximum response time. The third heuristic, maxWeight, weights edges by the sum of the number of edges waiting at each of its endpoints, and schedules a maximum weight matching in each round. This performs reasonably well on both average and maximum response time, and so might be the best choice if trying to keep both values low. We conclude our talk with discussion of some open problems. This paper explores some of the areas of flow scheduling on a switch, and much work remains in several directions. One direction might be to improve the approximation ratio without a further increase in resource augmentation, or to eliminate the need for resource augmentation entirely. For offline as well as online algorithms, it is not clear that resource augmentation is necessary to achieve good approximation or competitive ratios. A different direction is whether or not similar results can be achieved for other network topologies like trees, or more general types of flows like coflows. We thank you for taking the time to listen to our talk. The title of our paper is Scheduling Flows on a Switch to Optimize Response Times. The authors are Hamidreza Jahanjou, Rajmohan Rajaraman, and David Stalfa. Thank you again.